Hello, my name is Chris Fitzpatrick, and this is my test wrapper explanation for problem 2. So the question is, an insulating rod of length L is uniformly charged with negative charge negative Q. The rod is placed on the y-axis so that one end of the rod is at the origin as indicated in the figure. And the question is, determine the electric field dE at observation location 0, negative h, 0 due to an infinitesimal piece of the rod dy. And in order to solve this problem, first you must find lambda, which in this case, okay, 1 second. All right, so first you must find lambda, which in this case is equal to negative q over L. And then you must set dq over dy equal to lambda, which then leads to, let's see, lambda is then equal to negative q over L multiplied by dy. And from there, you must get the vector r for dq, which is equal to the observation r vector minus the origin r vector, which is 0, negative h, 0, minus 0, y, 0, which is then equal to 0, negative h minus y, 0. And then from there, it's pretty easy to get d, which is equal to k, or 1 over 4 pi epsilon 0, sorry about that, k dq over the magnitude of r dq squared multiplied by the unit vector of r dq, which is equal to k, or 1 over 4 pi epsilon 0, multiplied by negative q over L, dy, divided by, let's see, with negative h minus y, magnitude of that would be equal to h plus y squared. And let's see, the magnet, or the unit vector, would just be 0, negative 1, 0, which then makes dE equal to k, or I'm gonna change it to 1 over 4 pi epsilon 0, just so that we all know what we're talking about, multiplied by q times dy over L multiplied by h plus y squared. And this is in the y direction, the positive y direction. And written out in vector form would be as such: 0, 1 over 4 pi epsilon 0 times q dy over L h plus y squared, 0. So yeah, that is part 1. Next, part 3.2. Determine the net electric field at the observation location. And the way to do that, E is equal to the integral of dE, and is the integral of a rod, and the integral of the rod formula is from 0 to L of k q dy over L h plus y squared. In the y direction, I'll add that in later, which is equal to, well, you remove all of the non-y variables out of the equation, so it becomes k q over L times the integral from 0 to L of dy over h plus y squared, which is then equal to kq over L multiplied by 1 negative 1 over h plus y from 0 to L, which is then equal to kq over L times 1 over h minus 1 over h plus L in positive y direction, or in vector form again, kq over L 1 over h minus 1 over h plus L 0. And last but not least, we have the third part of the problem, which goes, a second identical rod is placed on top of the first forming a T as is indicated in the diagram. Use the new net electric field at the observation location. You can ignore the thickness of the rods. And using the net electric field formula, you've got E I'll just call them E. E vert plus E hor for vertical and horizontal. And we found the horizontal one in the first part of the problem. Now we just have to find the vertical one. And it's fairly simple. You've got so the horizontal one we found first, so that's kq over h times h plus L, and in the y direction, so y hat. And then you've got the vertical, which is kq over h plus L times the square root of h plus L squared plus L squared over 4, also y hat. And then adding it together, and just for the sake of clearness, I'll be using 1 over 4 pi epsilon 0 again. So you've got I'll just have it in vector form to begin with. Right, 0 q over 4 pi epsilon 0 times h plus L multiplied by 1 over h plus 1 divided by the square root of h plus L squared plus L squared over 4. And that kind of looks like a 9, so I want to make sure that that visibly looks like a 4. All right, and it is in all the way directions, so yeah. All right, that is it for this video. I hope it was clear, and hopefully I can solve problems like these better in future assignments. Yeah, thank you for watching.